Hi everyone and welcome. In today's video, we are going to take a look at an application of antiderivatives and indefinite integrals as it relates to solving a very basic type of differential equation, and we're also going to take a look at something called initial value problems. So let's first understand what even is a differential equation. So in earlier math courses, you probably are familiar with the idea of solving algebraic equations that are equations that involve x and like powers of x squared plus x equals like 0. Well, a differential equation is going to be an equation that relates an unknown function and its derivatives. So instead of having like x squared plus x equals 0 and solve for x, you're going to have something like y prime plus y equals 0. And we're looking for this very special function that when you add its derivative with the original function, you get 0. So that's really what a differential equation is. It's an equation that relates an unknown function to its derivatives. And we're trying to find what is that unknown function that satisfies that equation. Now, this entire course is taught on differential equations, but right now we're just going to focus on a very basic differential equation, which are differential equations of the following form. So this differential equation says, find an unknown function y. So the unknown function here is y. So find this special unknown function y that when you differentiate it, you get a given function f of x. So f of x is going to be given to you. It's going to be like sine x or something. It's going to be some given function. And we're asking, find me a function that when I differentiate it, I get this given function. In other words, antiderivatives are solutions to this basic differential equation. The unknown function is y equals capital F of x, that when you differentiate, you get this lowercase function f of x. And so the solution to this differential equation is an infinite family of functions denoted by capital F of x plus c, where capital F is some particular antiderivative of lowercase f. And so if you're not familiar with this concept of antiderivatives, then I encourage you to watch the previous video where we discussed all of this along with some antiderivative formulas. But continuing, if you have an entire family of functions, you can specify a particular member of the family by imposing an initial condition. That is, we know that these functions are going to be like just shifted copies of one another. And we're looking for a particular member of the family that contains like a particular point, x naught, y naught. So you can go ahead and specify this initial condition is what we call it. The solution curve must contain this point, x naught, y naught. And that will give you a single unique solution to this differential equation. And this is very common in real life problems, like physicists might specify the initial velocity or initial position of the given function. And so that will narrow down the most general solution down to a single solution that actually contains or satisfies that initial condition. Now, a differential equation together with an initial condition is called an initial value problem. Now let's take a look at how to solve these simple differential equations along with a given initial condition. In the first example, they want us to solve the following initial value problem. dy by dx is equal to sine x plus 2e to the x, subject to the constraint that the solution curve must pass through the point 0, 2. So to be super clear here, we're trying to look for an unknown function y, right? So y is the unknown function. We're looking for this very special function y that when you differentiate it, you get sine x plus 2e to the x. So you see now, like it matches the previous form, dy over dx equals f of x. They've given you f of x. It's a known function. And you're looking for something that differentiates into this. In other words, you're looking for the antiderivative of this function, and that's going to be infinitely many functions, but you're looking for the specific one that passes through this point. This motivates a two-step process for solving these kind of initial value problems. The first step would be to find the most general antiderivative. Well, the most general antiderivative is given by the indefinite integral, where you take this function to be your integrand. And to solve this integral, we can just take the antiderivative of each component. The antiderivative of sine is minus cosine, and then the antiderivative of e to the x is itself e to the x. And then you can stick the constant right there. And don't forget to add the constant of integration, because the indefinite integral represents the most general antiderivative. It represents an entire family of antiderivatives. Now we're looking for the particular member of this family that goes through this point, right? They're all shifted copies of one another. We're just looking for the one that contains this point. So to satisfy the initial condition, just plug in the given point, plug in 0, 2. We must satisfy that. So I'll take this function and I'll plug in x equals 0 and set the output equal to 2. That's what we're doing over here. We're plugging in 0, as you can see, and we're setting the corresponding output equal to 2. Cosine of 0 is 1, but there's a minus here, so we get minus 1. E to the 0 is just 1, but there's a 2 over here, so we just get 2. And then plus c. And all of this expression is supposed to equal 2. And then now you can just go ahead and solve this simple linear equation. The 2's cancel, you bring the 1 over, c is equal to 1. Therefore, the solution to this differential equation is going to be y of x is equal to negative cosine x plus 2e to the x plus 1. So this is the particular member of the family that will satisfy both being an antiderivative of this function and passing through this point. Let's take a look at another example. This one is a more application-focused problem, and that's really what differential equations are all about. They model real-life situations. So it says that a car is traveling at a rate of 88 feet per second when the brakes are suddenly applied. And so the car begins to deaccelerate at a constant rate of 15 feet per second squared. And we need to figure out how long it takes for the car to come to a complete stop, and also how long does the car travel during this time that it's braking. So to solve this problem, we need to introduce some variables and some functions here. So let t be the time in seconds since the brakes are applied. That is, we are going to start measuring time as soon as the driver hits the brakes. So time t equals 0 corresponds to the time when the driver actually puts his foot on the brakes. Now we were given that the car is traveling at a rate of 88 feet per second before the brakes were applied. So at the time when the brakes are just being applied, the initial velocity is going to be 88. And then also we know that the car is deaccelerating at a constant rate of 15 feet per second squared. So deacceleration means negative acceleration. So the acceleration function is fully determined. Its a of t is always going to be a negative 15. Notice the difference. Over here I have a given point. The initial velocity is 88. Whereas for the acceleration I have the entire function determined. Acceleration is always a constant negative 15. Now in the first part of the problem, we have to figure out how long it takes for the car to stop. Well, when the car stops, the velocity is going to be 0. So we need to find the velocity function and set it equal to 0. To determine the velocity function, we have to notice that the derivative of velocity is acceleration, right? The rate of change of velocity is acceleration. As a result, the antiderivative of acceleration is going to be the velocity function. And so in other words, we have to solve a simple initial value problem. We have to find this unknown function v, that when you differentiate it, you get the acceleration function, which is negative 15 in this case. And subject to the constraint that the initial velocity, v of 0 is equal to 88. So this is the problem phrased in terms of an initial value problem. So let's go ahead and find the antiderivative of acceleration, which is the antiderivative of negative 15, and that would just give us negative 15t. Because a linear function differentiates into a constant, right? And the derivative of a linear function is the slope, and so you would get back to the integrand. Or you can think of it in terms of the power rule. Think of this as t to the 0. You add 1 to the exponent, you get t to the 1, divide by 1. And you can think of it like that. So this has given us an entire family of velocity functions. But we're looking for the specific velocity function that contains the point 0, 88. So all we're going to do is just plug 0 into this and set it equal to 88. So I plug 0 into the function and I set it equal to 88. The 0 over here cancels with a negative 15. And so therefore c is equal to 88. Therefore, the particular velocity function that we're looking for is negative 15t plus 88. Finally, as we discussed, the car stops when the velocity function is equal to 0. And so that means we have to set this expression equal to 0 and solve for t. So you can just bring the 15t over and then divide 15 on both sides, and you'll get time is equal to 88 over 15 seconds. And since the way we're keeping track of time is that time t equals 0 corresponds to when the driver first hit the brakes, this is exactly how long it took the car to come to a full stop. It's going to be 88 over 15 seconds. Now let's solve part B. In part B, we have to figure out how much distance is covered during this time. So in terms of mathematical thinking, we just need to find the position function evaluated at 88 over 15. That will tell us what the position of the car is at this point in time. So that means we need to find the position function. And the idea is very similar. We know that the rate of change of position, right? The derivative of position is velocity. And so that means the antiderivative of velocity is going to be position. Now we found the velocity function in the previous part. It was negative 15t plus 88. So let's go ahead and find the antiderivative term by term. Each one can be done using the power rule. We add 1 to the exponent, so it becomes t squared, and divide by the new exponent. As a result, you get negative 15 over 2 t squared. And this constant number becomes a linear term. It picks up the t factor, so 88t, and then plus the constant of integration. Now, really what we're trying to do here is solve the following initial value problem. We're looking for this unknown position function, s, that satisfies the following differential equation. That is, when you differentiate this position function, you're supposed to get the velocity function, which is negative 15t plus 88. And now I claim that it's subject to the condition s of 0 equals 0. And you might be a little bit confused where I got this because this wasn't in the original problem statement. But remember, we can model the problem however we like. And just like how we started modeling time since the brakes were first applied, well, I can also insist that I model distance since the brakes were first applied. And then as time progresses, while we're braking, the distance function is going to model how much distance is being traveled during that time. So using this initial condition, we just plug 0 into this function and set it equal to 0 to solve for c. So I plug 0 in here, and set it equal to 0. And in this case, everything will cancel out and c equals 0. So the particular position function we're looking for here is s of t equals negative 15 over 2 t squared plus 88t. And finally, our strategy was to plug in 88 over 15 into this function to give us how much distance has been traveled during the time that we were braking. It turns out to be 258 feet. And that completes the full problem. And that brings us to the end of today's video, in which we covered a very simple differential equation whose solutions were just antiderivatives. And we also looked at solving initial value problems, which is just a differential equation along with an initial condition, so that among all the possible solutions to that differential equation, we're looking for the solution curve that passes through that given point. And so you get one single unique solution. That's really all an initial value problem is. In the next video, we're finally going to start looking at the fundamental theorem of calculus and answer some unanswered questions that we have about the connection between the definite integral and the indefinite integral. And so I hope to see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.